morning session, and the second speaker is Bernardo Uribe from Universidad del Norte, who will talk about Morita equivalence and diffusion calculus.
So good morning, everybody. Thank you, Ernesto and Jaco, for the invitation. It's always a pleasure to be here, and more in this conference honoring Samuel Gitler, a very charismatic mathematician from here in Mexico. So I'm going to talk about this subject on which I know that perhaps some of you will not understand any of the words that I put on the board. So I'll try to somehow guide you through the understanding of these words, and I will finish with a specific classification of these point diffusion categories. So let me start with the object that I'll work with. It's a very nice simple object. So I'll have a finite group as a start, and a 3 cocycle. So I put it here with coefficients in C star. So what does this mean? I will tell you in a while. How could you think of this information? But anyway, so with this information I can construct very simple tensor category that is defined in this way, on which the objects, we should think of them as vector spaces, which are labeled by the letters of the group. So each of these VGs is a vector space, complex vector space. Complex vector space. So we simply take, for every letter of the group, take a vector space, and homomorphisms between these vector spaces should fix the label. So you only have homomorphisms for each label, but you can tensor these objects. So, and basically you use the convolution product, or you use the product of the group, and you simply say that this is the following object on which I'm using the tensor structure of vector spaces. So I'm just simply saying that if I have say a vector space only based at G and another vector space only based at H, when I tensor them I get something based at G times H. So the group structure is somehow on the labels, and then I just tensor the vector spaces. So with this I can construct this tensor category, but then I use the omega to change the association, the way the associator goes. So I then simply say that VG tensor W K tensor C sub L, and I just decide a specific isomorphism from the way I do the association of these things, and I just simply take the cocycle that I have here to somehow twist this association. So I just simply use this element, which is an element in the complex number variable, and I take this. So it's simply the way we associate these elements, but then we just twist it a little bit. So as I said, then you might think, well, this is some sort of an enlargement of your category vector spaces, and I'm just somehow telling you how we are doing associators, and then this satisfies some pentagon identity that I'm not going to write, but this pentagon identity, basically measuring how you're going to put these objects together, is equivalent to saying that this element omega is a cocycle. It's equivalent. So the cocycle condition is telling you that it satisfies the pentagon identity. Now this is a very simple tensor category. Let's say one of the most simple ones. You take a group, you take a cocycle, and you construct a tensor category. Now from these tensor categories, you can construct modules out of it. So I'm not going to give you all the diagrams that this may have, but you have to see a tensor category, and let's have a tensor category like this one, on which the space of homomorphisms is a C-linear space. So these types of tensor categories, I can construct module categories. So this is over C, in which, like in this case, the homomorphisms are C-linear spaces. What is going to be then a module over this tensor category? Well, if you haven't thought about this before, then you should think that we have an algebra and we're going to construct a modular or an algebra. The idea is the same, although we have to take care that all these things are categories and whatnot. So what is going to be this? Well, it's going to be a bifunctor from this tensor product of categories to this one, satisfying a lot of information, but the point being is that I could define it. And one of the specific information that I have in here, so I'm going to put it in this terminology, is a way to define the way we are acting now. So now, as we are in this world, we don't have somehow the explicit way to do the association, so we need to define explicitly what happens if I take elements of the category and I tensor them in the category, and then I act them on the module. What is the relation between act on the module and then act again on what is on the module? Then I need to prescribe some isomorphisms, and these have to satisfy some pentagon identity. So everything somehow is weak now, it's not strict. But anyway, these are these modules. So we can construct the modules. The modules in this case are simple to describe of this category. And the question is, how do I know when two of these categories of this type do have equivalent categories of modules? Like in the same sense, like in algebra. So when are two algebras Morita equivalent? When do they have the same or equivalent categories of modules? So this is the question that I want to answer. So if I have two of these G omega, two different groups with two different twists, when do they have equivalent categories of modules? No. Somehow this is the question. So I define some categories, I have some modules, I have some decomposable modules, I have some structural pieces that build all the modules, and then I have a category. Now, what are the conditions that I need to impose on G and omega such that the categories of modules are the same? Of course, if I have the groups that are isomorphic and the cohomology classes are somehow one map to the other by the isomorphisms, of course the categories are equivalent. But the question is, how could I determine which different groups and which different twists will give me this? Now, let me just somehow tell you some sort of implications of this thing that relates to some construction of Drinfeld, of the Drinfeld double, and of some constructions of Witten and Akrams and whatnot. So what is the center of one of these categories? If I have a tensor category, there is some sort of analog of the center of an algebra, which is the center of one of these categories. So I will tell you only the objects for you to have an idea. So objects are a pair, so where X is an object of the original category, and eta is a bunch of isomorphisms. One for isomorphism for each element. So and right the same. So what does this mean? That for each y in objects, I need to tell you a specific isomorphism from x tensor y to y tensor x. So it's a way to somehow shift the coordinates. And so the center precisely are the elements on which I know how to do this. So if you think of the center of an algebra, are the ones on which are commuting with everybody. So then this object is a tensor category. But what is more important is that it's braided, because somehow at having chosen this object, the braiding comes automatically embedded into the definition of the objects. That's somehow what is very, very important. So this is braided. So in the sense, why is this braided? Because if I go from x eta to y epsilon say to y epsilon x eta, some sense. I just simply use the way to go from there is basically using the starting one. And so the braiding is already embedded in the information of the first object. So then this category is braided tensor category. Now in the case of that we are studying here, this category is well known, and it was constructed by Drinfeld himself. So I could simply take the center of this tensor category, and this category is the information, or with this category I can construct a quasi-triangular Hopf algebra, which is called the twisted Drinfeld double of the finite group. I don't know how to write Drinfeld, but since many of you are here, some people write with something here, which I don't know why. Perhaps tell me.
Well, it stands for something in Russian which is not pronounced.
Okay. So then this is a specific quasi-triangular Hopf algebra. So it's something like a Hopf algebra, but on which the multiplication is not associative on the nose, but it's weakly associative. It's a coalgebra, but moreover it has a braid, so it satisfies the Yang-Baxter equation. So that's the importance of this object. Now, this object also was used or discovered by Witten and Daycraft, because this is a way to construct a toy model for Chern-Simons, or a finite dimension, or a finite group Chern-Simons theory provides or give us this algebra. So if I have a group and I just construct Chern-Simons by using this group as gauge group, and I use this omega here. Recall that omega is a class in H3 of the group with C-star coefficients, but this is the same as H4 of BG with integral coefficients. So then we know Chern-Simons, we are in the right place, because we take the class that's coming from the third homology of the Lie group. If we had a Lie group and we construct Chern-Simon theory, this is the object that appears and gives us a topological field. Now, the point being, what is very important now is that when or how do I define, how do I say that two tensor categories are Morita equivalent? Of course, I could say that the categories of modules are equivalent, but somehow this was the definition that appeared first, or the definition that was used by the people in tensor categories. So prior to that, so let me take mu a decomposable, like a simple object, module on the tensor category C. So then I could construct, like I do in the algebra world, I can construct functors from this category from M to M. Basically, functors from the category M to itself, or like we to think of endomorphisms in this appropriate category. And this is again is also a tensor category by the composition of functors. And let me just simply denote it by this, some sort of dual of the original category via mu. So the definition now is two tensor categories, B and C, are called Morita equivalent. If D as a tensor category is equivalent to C dual via some decomposable model. So the way to think of this is well, give me some sort of module in your category, taking endomorphisms. The category you're getting will be Morita equivalent to my original one. So then with this information in here, what is quite interesting is the following result, Ostrich and some other people, which is the following. If I do have two tensor categories which are Morita equivalent, their centers are isomorphic, which is so, and this is an if and only if. So if I have C and D Morita equivalent, if and only if the centers of these categories.
How far is the center from Hochschild?
Okay, wait. Let me finish writing R. But I need to say what type of equivalence. So this is Morita equivalence there, and here's braided equivalent. I need to use the braiding. Otherwise, I cannot reconstruct the original category. It has to be using the braid. So now the question of Ernesto: how far are these people far from Hochschild? In the sense that Hochschild is the derived center of an algebra, or what
Well,
center?
for a category, Hochschild of a category.
Well, it depends on your category, and this is the naive center. This is the zero part. This is H naught. You haven't derived it. In this case, we don't need to do any derivations. But if you choose any category, this would be what is in the zero part.
But I mean, in this.
I don't. All these things here are exact. So then, if everything is exact, so then this is just the H0 part. So but if you do it more general, then you need to see whether you have the exact sequence or not. You need to derive it. I haven't derived it because I don't need it. It's not the cohomology of the group is not appearing here.
Okay. So yeah, I guess this would be relevant if it was a DG cat or something like that, or.
Yes, or if you would be detecting modules of the group, but you're not detecting any module of the group. It's not appearing somehow.
Okay.
So then, if we accept this result, which is very nice, I mean, if you have that the two centers are equivalent, then you may reconstruct Morita equivalence. Then the question is, if I want to classify all these field theories, if I want to classify these quasi-triangular algebras that are braided, if I want to say when two of these are isomorphic, it would be the same as calculating when are the original information Morita equivalent. So then, simple thing, these twisted drifted doubles are isomorphic as braided algebras, as braided Hopf algebras. If braided algebras, so this is braided. So if and only if these two categories are Morita equivalent. So in some sense, if I was, as I was telling Hugo in the intermediate, if I do the Chern-Simons construction for this group and this twist, or if I do the Chern-Simons construction for this group and this twist, I get the same physics, I get the same topological quantum field theory. I cannot distinguish the two from the original information because what I detect is this, which is the center. So which pairs of groups would give me same somehow topological field theories, and that's what I want to answer here. Now these objects have appeared in several disguises, and so let me give you one disguise that appeared. This appeared when I was almost a student. So if one takes representations of the twisted different double, now note that it's the same as representations of the center of this category. Many letters, no? But I have a category, they have modules, the modules, this is what I call representations, and I could take isomorphism classes of these representations, and this becomes something that Ernesto and I have studied. This is what my advisors called the twisted, or the stringy, twisted K-theory of the orbifold, or the kaleidoscope. So this was is a way to endow the K-theory associated to a group with a ring structure, and if I start with a 3 cocycle, there is a way to get via the inverse transgression map some K-theories, and this is the, let me put it somehow, the way that is constructed. So I take the inertia groupoid of this, so G acting on itself, and then I put the transgression of this element, and at least as a module this is the way it's defined, and then the multiplication is some sort of pull-push construction. But so this had appeared before, and again, if I do have 2 of these Morita equivalence categories, then the algebra that I could get are automatically isomorphic. Now, although one could try to do it at the algebra level, what is the isomorphism, it turns out to be quite complicated because I'm doing things at the level of the center. So that the center somehow makes these calculations very complicated. But somehow, let me somehow change a little bit and tell you one way to understand of a group and a 3 cocycle. And the way to think, one way to think about this is in the language of the 2 groups, the language of cross modules. And so having G and a 3 cocycle is having some sort of specific type of weak 2 group or a cross module. So it's not far away from perhaps things that you've seen. So let me just go to this world. So this category has it is quite big, but it has some sort of a skeletal version of it. So namely, I just choose one object for each isomorphism class, only one, and I just simply basically reconstruct the information of the category out of this specific minimal version of the category. So I just take one object for each isomorphism class. Here there are many, because there are many automorphisms. But if I do that, then the skeletal version is simply, I call it like this. So the objects of this category, its objects, are just simply the elements of the group only, not vector spaces, right? And I don't allow any morphism from any different object to another object. Or if I want to say morphisms from G to H in this category is C if G is equal to H, and 0 if G is 0 than H. Some sort of. So I just simply say that the endomorphisms of any object is C, and there is no morphism from any other. And if I do this, then I can. So I have objects, I have my morphisms. So the automorphisms, of course, the automorphisms of any object is simply C star. So I have a group on the base. At each group, I have automorphism C star, and the omega is the associator in the same way. So I just decide G tensor H tensor K is given by omega of G HK by G tensor H tensor K. So with this information, this category, it is equivalent to the one on top. It is minimal, and if you see what is the information I have, the information I have is a finite group, an abelian group, and a 3 cocycle. And if we know what is the classification of the isomorphism classes of cross modules, this is the information that is precisely on the isomorphism class of a cross module. So what is a cross module? So let's just simply go to this world of cross modules. These were described by Whitehead at understanding the homotopy type of the 2 types of topological zero group complexes that are connected and that are whose homotopy groups different from 0, the pi1 and pi2, only that. So we want to understand what is the information that is encoded in these topological spaces, and he showed that is the fundamental group, the way the fundamental group acts in the second homotopy group, and the one element that says in something how these things are twisted, which is the first element of the positive tower is just an element of the third homology group of the fundamental group with coefficients in the pi 2. But so what is a cross module?
G is discrete or finite?
G in this case, in my talk will be finite.
So this is, in this case, really like a line bundle of the three-loop space of BG.
Yes, but a specific one.
Yeah, this line bundle of the three-loop space of BG.
Yeah. Yes. This line bundle is the transgressed.
Mm-hmm.
That lives on the center again. Mm-hmm. But from this some sort of universe of topological quantum field theory of 3 to 1, 0, this is what lives on the point, and you're telling me what lives on the circle. But if you have what is this hypothesis? If we have the information of a point, we have the whole 3 to 1, 0 information of the field theory. The thing is that we know what it is on a point when G is finite, and as I was telling you, we don't know what is the information when G is a Lie group. We know what is the 3 to 1 theory, but we don't know how to pull it down to 0.
Well,
but I don't know.
Jacob Lurie gives this complicated algorithm.
Okay, maybe he knows, but I don't know. So then what is a cross module? So we have a pair of groups and a homomorphism. These are groups. And an action of G1 into G2. And let me call elements in here alpha and beta, and let me call elements in here by letters A that satisfy some equations. So let me just say that the action of G into is via some action on the right. So the equations is, and let me just simply say that this element goes to with an underline. It's just a simplified way to say what is a cross module. So I have an action, a right action of G1 into G2, and these are the equations that you need to satisfy, which is if I take an element alpha and I act by A, this has to be the same. Oh, you need to. Oh, you see, I'm doing it. I need to be careful. Yeah. If I have an alpha and I send it to G1 and I act by A by conjugation, has to be the same as taking alpha, which is on top, act by the element here, and push it down. And the other equation is if I take an element beta and I act it by the image of alpha, has to be the same as beta of alpha, the conjugation. So when I put here underline, means it goes here. When it goes here, it acts on here. Well, this is very complicated, I know. The first time you see this, it makes no sense. But there are some structures that you need to put. Basically, that the conjugation action of G on itself by the automorphism has to be somehow compatible with this. An example of this, perhaps the most simple example, is take G in G2 and take automorphisms of G in G1, and simply the map from here to here is the inner automorphism that G defines. So just simply take G, send it to the adjoint action of G. And this is the most somehow known cross module. The kernel is the center, the co-kernel is the external automorphism group. Now, the thing is, these cross modules, I just define them like that. You see there is no twist in some sense. The category of cross modules, there is a very easiest description in another world. So the category of cross modules is equivalent to the category of two groups. So what is a two group? So a two group is a group object in groupoids. So it's a group object in groupoids. Group object in groupoids. Groupoids, discrete groupoids. I'm not putting here topology for the time being. So what does it mean that it's a group object in groupoids? Means that you have a G is a groupoid, and this groupoid has to have a multiplication and has to have an inverse map. So you need to have a map.
But why it is not a group object in groups?
Also,
Of course.
there are gazillion ways to describe a cross module. So yes,
A group object in groups is going to be an abelian group, actually. And
a
that's-
group object in groups is an abelian group, and that's the reason why. Well, so for the people not knowing, so a groupoid is a category in which every object is invertible. So it has some objects, G naught, some morphisms, a source and a target and multiplication, and some math going here, which is the way that you choose the identity. So that's a groupoid. But now if I take a group in groupoids, means that all this machine, or this object, has a map of groupoids, which is called the inverse, and moreover has a map of groupoids, which is the multiplication, which satisfies the diagrams that a group satisfies as diagrams. So you take what is the definition of a group diagrammatically, and you put in the category of groupoids. Now you do that, what you get is equivalent to a cross model. So in some sense, all these equations will appear if you entangle what is a group in groupoids.
And what happens if you don't have an inverse here?
Then, well, at least you are not able to show that the kernel of this is abelian. You need the kernel of this to be abelian. As you said, a group
Object in groups.
a group object in groups
Of course.
is an abelian group. So I need to have the inverse to show that what is on top of the identity is abelian, and that's somehow the kernel of this thing. So perhaps, and I like this description because it's simple. It's simple. So all the information has to be here, and then you just make it happen there. So how to go from one to the other? Well, there is a way to go from one to the other. So if I have one of this information, if I have a cross module, then if I have a cross module, so the way to construct a groupoid is my G naught will be G1 acting on G2, and G1 will be G2, and the way to define the source is simply the other way around, sorry. This is G1, this is G0. The source will be simply forgetting the G1, and the target is using the action together with the delta. The arrow goes down. Yeah, 3 arrows going down. But anyway, so you simply construct it using the action of this into this. Those are the morphisms, and the objects will be this. G1. It's to be G1. Yeah, and the way you go from G2 to G1 is using this data. Nevertheless, now we have this, but as you may notice, there is some information in this cross module which I can get out of it, which is the kernel of delta and the co-kernel of delta. So it turns out to be, so I simply define out of this cross module, I could define the co-kernel and the kernel. The kernel will be an abelian group, and this is just a group. And it turns out that the information that classifies the cross module is this co-kernel, this kernel, and a 3 cocycle. So the class, the isomorphism class of the cross module is given by this co-kernel of delta, the kernel which is abelian, and some element we call L of the co-kernel with imagine the coefficients in the kernel. So what I'm trying to portray here is if we have the category cross modules, if I want to understand what are the cohomology, somehow the isomorphism classes of cross modules, the information that is somehow relevant for the isomorphism class is the co-kernel, which we think of it as the fundamental group of the 2-type associated, the kernel, which is the second homotopy group of the 2-type associated, and the cocycle in here, which is the first Postnikov invariant, the Postnikov tower. Good. So having this in mind, when I construct this category that I told you, B, G, as I say it again, C star, or sorry, BG omega, this tensor category, we should think that is a specific kind of cross module, where it's a specific kind of two group, a very simple one, on which the two group associated is given this G would amount to be to the co-kernel, C star would amount to be to the kernel, and the omega would be the invariant on the C3 of G of C star. So what I'm trying to portray here is that if I give you this category, it's completely related to two groups, it's completely related to cross modules. It's just a very simple, somehow, cross module on which G is acting trivially here, but it has the advantage, because I'm taking the kernel to be the whole C star, that it gives me a tensor category which is based on the complex number. So in some sense I could go to the world of fusion categories and work there, because this two group has this automorphism group of the objects, which makes it then a C-linear space. Good.
And conversely, if you had a more general situation, could it be like a non-abelian germ on the co-kernel?
Wait, let's start again. On the more general...
Conversely, so this is a particular case.
Yeah, so this is a particular case of a two group or a cross module. It's a cross module or a two group.
That's right. But conversely, if
conversely means if I have
a cross module, a general one, could it be the same as a non-abelian germ on the co-kernel of the cross module, seen as a stack?
Well, the cross module is the two group, and
That's right.
And so.
But
why am I doing all this to get into here? In order to go to the world of tensor categories in which the morphisms is a C-linear space. You see, so because any cross module in general, no. The automorphism of a point is some abelian group. I don't know what it is. But in this case, it's C star, therefore I could go to the world of fusion categories, and then I could work there, which I have somehow more room to play. But what I wanted to portray is that G and a cocycle, you should think of it as a two group, or as a cross module, or as some sort of two type of some sort.
Yeah, I'll ask you later. Yeah.
Okay, yeah. Good. So somehow, let me go to how this thing goes. So let me go back to my category. My category is this category that I put in here. And I basically tell you, so I have this category, is, as I said, it's just the group itself, and it has some association. So what is any decomposable module? So the information for a module in here, so a module, or any decomposable, is given by an orbit type. So G mod a subgroup, so it has to be some sort of orbit type. Why? Because at the end, these are the objects of the module category, and G is acting on the objects. So it has to be some G set. The decomposable will make it transitive. Therefore, it's one of these things. And the other information is some specific map. That what it does is that it tells me that in some sense, what it tells me is that I need to satisfy some pentagon isomorphism or pentagon identity, and it tells me that this is the information that I told you how to multiply and has to satisfy this equation. One of the conclusions of this thing, simple, that omega has to be trivial on the subgroup as a cohomology class. So if I want to have a module that is decomposable, I need an orbit type, but moreover I need the isotropic group of the orbit type at some point to trivialize the condition. This is somehow just because I need the pentagon too. So if I want, say, a point, just a point, I would need the cohomology class to be trivial. Good. So with this in mind, I could somehow If I put some other conditions, let me put some other condition. If L as a subgroup is normal, so L is normal, well, let me call it not yeah, let me call it A there, and abelian, then this dual category, so I put this G and I put this omega, and I take the dual associated to this module, then it's again one of these categories. Then this category is equivalent to some other category of G hat and omega hat. So these are some conditions that I need to satisfy, and now I'm going to tell you the result, and we can somehow we can distinguish some groups on which the centers of these categories are equivalent. So this is the theorem. And this is somehow the homological information. So let me tell you what is the homological information. Since I have here a normal subgroup on which is abelian, I could take the extension. So if I have an element F, which is a second cohomology of, let me call it the kernel, I'm going to call it K, with coefficients in A. So this object is going to generate this group. And if I have another one, which gives...
Who kernel?
Sorry?
Who kernel?
Let me just put it here. So I have A is a normal subgroup of G, and this is a cokernel. Let me call it K. So I could construct this G as an extension of K by A, where K is acting in A. So I construct this cohomology class, and I construct another one, but now on the dual. So this is some sort of abelian duality on the theories. So A in this case is the dual of the group. And with these two elements, I can construct another cocycle, and this is where the group cohomology comes into play. So I could define an element which is the following. This element takes values in A hat, this takes values in A, and I can compose them. So I define F with elements K1, K2, dual evaluated in F of K3 and K4. So this element in here is a cochain, 4 cochain of K with coefficient C star. If I know that this is closed, I'll tell you what happens. So if I have, so let me put it this way. I want to understand when two groups and cocycles give me the same information in the center. And I'm going to tell you the information that I need to have. So the information I need to have is that G is an extension of A, and that the dual is an extension of the dual. How the groups are related? Well, I need that the classes that define these groups are related via this equation, namely this product has to be trivial in cohomology. If I have this information, then I could say the following. So this is the theorem. This is by me. So I just simply, if I have this information, then take G to be the extension of K by A via this F. Take G hat to be the extension of A dual by F. So these are two groups. One is extended by A, the other one extended by A hat. Different groups. I can define an omega, and the omega is simply defined. Omega is defined by F hat and epsilon, and I'll put it simply F hat times epsilon in an appropriate way, and omega hat is F times epsilon. If I have this information, the two categories are Morita equivalent. And moreover, any equivalence is of this type. And any Morita equivalence is of this type. So if I do have two Morita equivalent categories of this sort, means that I could construct it in this way. Look, but the way G hat has F hat, and in its twist, in the twist, the information of F, and in the twist of G is the information of F hat. So the the twisting of the group goes to the twisting of the class, the twisting of the class goes to the twisting of the group. This is reminiscent of T-duality in physics or in K-theory. This is just some sort of version of T-dual. So let me give you the examples. So example 1. The simplest example we can construct is with G, I'm going to take it Z2 times Z2. So in this case, the abelian group is going to be Z2 and the K group is going to be Z2. And G hat will be Z4. They both live, these are the two tensions of Z2 by Z2. Now I'm going to take omega and omega hat. So omega hat will be, in this case, trivial, because somehow this group is already twisted and this is untwisted. So omega is going to be the following class, which is x squared y squared, which is an element on the fourth cohomology group of BZ2 cross Z2 with coefficients in the integers. So I'm taking an element of degree 4 as an element of the 3. And in this case, we have that the Drinfeld double of x squared y squared of Z2 cross Z2 is isomorphic, is a braided algebra to the untwisted of C4. This is somehow the simplest of the simplest examples. So, on which tells me that the untwisted group, but twisted by the 3 class, is the same as the information given by the twisted group, but somehow the information of the twist of the Chern-Simons theory is not there. So if I would like to extrapolate these two Chern-Simons, if I have some sort of information on the group which is untwisting something, like SU2, which is untwisting SO3, therefore the Chern-Simons associated to SU2 should be equal to the Chern-Simons of SO3 cross Z2 with some twist. This I'm not able to prove because this procedure will not fit for the Lie group case. Let me give you an example for Alberto. The binary tetrahedral. No? So binary tetrahedral is the extension of the tetrahedral group, the symmetry of the tetrahedron, which is A4. So we have A4, which sits in SO3 as symmetries of the tetrahedron. And then, as Alberto was telling us, so we take the lift to SU2, and this is the binary tetrahedron group, and it's an extension of Z2. So, with this information in hand, the tensor category of the binary tetrahedral is Morita equivalent. It's the same thing, no? To the category of A4 cross Z2 with the appropriate twist that defines this extension. Name it the way you want it. This extension is defined by the second cohomology class. This is some sort of alpha that defines the second cohomology class of A4 with coefficients in Z2, coming from the pullback of the generic extension here. It's the second Stephen Whitney class. And this class, I could lift it to some class in here, and it tells me the theory you want it to the binary. The binary tetrahedral is equivalent to the non-twisted one. And as I said before, this is some sort of the finite version of what I was telling Hugo of the Lie group version, on which SU2 is twisted. It's an extension of the twisted version of SU2 by Z2, but I could lift it untwisted, but then I put some class there on which I do the Chern-Simons theory. So, of course, one could cook up many more examples. One can take, for example, the quaternions group. Untwisted is equivalent to some specific twist that I call B of the dihedral group, because the dihedral and the quaternionian group are both extensions of Z2 by Z4, where Z2 acts on Z4 by the non-trivial automorphism, and so this gives somehow a way to classify all possible fusion categories up to Morita equivalence. What is going on here what is going on here is that at allowing, so I have a group on the, say, on the bottom, and I have some sort of extra information on the, say, call it second homotopy group. When I take modules, I'm allowed somehow to shift some information of the second homotopy group to the first homotopy group and vice versa. Only if I do it with modules. If I see equivalence of categories, I don't see that. They have to be equivalent to P1, they have to be equivalent to P2. But at taking modules, I could intelligently somehow shift this information, but it has to be abelian. That's why I said the extensions are always, have to be always abelian. They cannot be non-abelian, because then this moving you cannot do. So to finalize, Ernesto says that Luri has a version of it, but to my knowledge there is no simple version perhaps of the Lie group case, in which I start with a Lie group, an element in H4 of BG, and I construct something out of it, a tensor category, whose center, and if I take the center and the representations, I get this twisted K-theory of Hopkins, Telemann, and Fried. This I don't know if there is the object on which one can perform this. If one has it, one can do the same business. Take the category, take the modules, take the Morita equivalence, and perhaps one can get all of these things through Lie groups. Anyway, thank you very much for listening.
Are there any questions?
For A5, for a binary, I consider a group is the same thing?
The same thing, as long as you give me an extension,
Which is abelian.
as long as the extension, which things abelian, I take the class of the extension and I push it on the other side up, and then I untwist it somehow. But somehow, it's not that I untwist it, it's that I put the twist somewhere else. Perhaps this could be seen as taking coordinates. I have group coordinates and cocycle coordinates, and I can swap them if I think of them in a democratic way. But if I don't think them democratically, some coordinates are on the first level and some other coordinates on the second level. But if I swap them, the twist of the group, which is a 2 cocycle, I shift them as a 3 cocycle on the other one. Okay. So give me an extension that is abelian, and this follows.
So this is related to splitting of equivariant cohomology theory?
Of a splitting of an equivariant cohomology theory. To what I was asking you yesterday. So Hiko is asking the following: if I have an equivariant cohomology theory generically, and then I take the coefficients of a point, namely the equivariant cohomology of a point, which is whatever it is. In the case of K theories, representations of the group. In the case of the equivariant cohomotopy theories, the Burnside ring. Whether first of all the group acts trivially on the coefficients. So he was asking me whether if this could be applied or used to the splitting in equivariant cohomology theories. The answer is I don't know. I see them. I see many similarities. This could be applied, say, for this Tate cohomology, equivariant Tate cohomology. Two groups with two twists that relate on this gives you the same Tate equivariant twisted cohomology, because somehow these are theories based on the tori, and basically one circle shifts to the other circle. But the way to prove it, I don't know how would it be. That is not by hand saying that this is the isomorphism, but I don't know about the splitting yet.
Sorry. Well, a natural question is, once you have solved the Morita equivalence problem, do you have a notion of tilting of these categories?
Oh, could you remind me what is the tilting?
Well, for example, in the algebra case, if you have equivalent module categories, the algebras are Morita equivalent, and you have a projective module that solves the equivalence. And well, tilting theory is like the same thing, but instead of using Hom and tensor, you use ext and tor, for example.
Yeah, somehow that's what related to Ernesto's question, whether this is the derived center or not, and this is not derived at all. So you're asking me what is the derived statement, and This is all exact here. I don't have extensions. I don't have. This is just somehow exact. So I could use tensor and because it's exact. You see, I don't have to resolve anything. I don't know if I answered.
This reminds me something else. You remember in our T-duality paper, it's really a triple product and then you go to double products.
It is a triple product that you
Or
got.
the multiplication of 3 things and then you go to 2 things or to 2 other things.
Yeah, so yeah, this is something that I haven't been able to do, but it's because
Because if this is a version of mirror symmetry or Kosul duality, then maybe A, K, A.
so if I understand correctly, Ernesto somehow is trying to put this into some diagram and then. So yes, this is somehow what I thought at the beginning. That this should be some sort of Fourier-Mukai transform. But whatever I try to do, Fourier-Mukai doesn't preserve tensor structure. And somehow I met Dimitri Kalein recently and asked him why on earth don't we care about the tensor structure of the category of sheaves on a variety? And he says, yeah, because then it's too rigid. Then if you want to preserve the tensor structure, it's basically not much what you can say. The classes are very small. But the thing we want to care is only the abelian structure, not the tensor structure. So the Fourier-Mukai is very well suited for that, for getting about the tensor structure. So because this is tensor, then when I do pullback, it's okay. When I do push forwards, I destroy my tensor structure. So it's not possible to do it using this Fourier-Mukai machinery. Although it's reminiscent, it's very reminiscent. Because I have a class here and I have a class in here and I pull them back and I relate them. But the way to go from one to the other is not pull push, unfortunately. Of course, there is also a line bundle, clearly line bundle, which is A and A dual, and that gives you a specific map. So the whole information is the same, but the tensor structure doesn't allow you to do pull push. Maybe I'm not understanding well, but it's done using the module, specific module.